in reputed journals and conference proceeding. She also sought after expert speaker, having delivered invited lecture at NIASA FDPs. And beyond teaching and research, she has actively contributed to the profession by organizing FDPs in association with Council of Architecture and Intact Heritage. She is associated with multiple professional bodies and editorial boards, including being an active member of the International Association of Urban Climate, Global Outdoor Thermal Comfort Studies Working Group, and the life member of INTAC and the Indian Society of Remote Sensing. Presently, she is working as Dean Academic in SPA Vijayawada. Now, I would love to call Dr. Lily Rose ma'am to deliver her session. Thank you, ma'am.
Thank you, Dr. Prashanti. I think after Professor Math's session for the past 4 days, I think whatever I'll be presenting today is just a drop in the ocean. But still, we have done few of such studies in Indian cities. I'll be presenting that. Let me just present my screen. I hope my screen is visible to everyone. Dr. Prashanti, am I audible? And
now it's visible.
Yeah, ma'am, it is audible.
Thank you. So today I'll be just giving an overview of this thermal comfort studies, outdoor, especially focusing on outdoor thermal comfort studies that have been done in few of the Indian cities. To start with, I think all these have been discussed earlier as thermal comfort differs, the indoor thermal comfort differs with that of the outdoor thermal comfort, and most of it depend on the personal parameters and the meteorological parameters. So the parameters that are used basically as I think Professor I.A. Vijayalakshmi had given a list of indices that are used both in indoor and outdoor thermal comfort studies. So this basically most of the studies are pertaining commonly used are PMV, PET, PIT and other things. So here we'll be focusing on all this. Why this is important is basically these studies would enhance the productivity. It has a significant impact on health. So we do have these thermal comfort affects the productivity, it affects the performance, it affects the learning and cognitive skills, health and well-being. So it is important in those. Just to give a brief on why indoor and outdoor are different. Indoor studies wherein we can have controlled temperature, controlled humidity. It's basically a steady state affair wherein all the indoor parameters can be controlled, and in the absence of direct solar radiation, wherein when it comes to outdoor comfort, it is very difficult because you cannot predict the outdoor state of environment. It is not in a steady state condition, and it depends. It also varies in terms of the expectation of individuals, and there are three basic parameters which differentiate indoor to outdoor conditions. Basically, in terms of physiological aspect, that is in terms of adaptive nature, especially people tolerate a larger variation in climatic conditions in the outdoors when compared to indoors. Though we have been in India, we follow that somewhere around 24 to 28 or 24 to 30 degrees is a comfortable range when it comes to indoors. But then in terms of outdoors, we do tolerate up to 32 degrees, depending on the geographical region where the city is located. And there is also this thermophysiological aspect, which also affects basically based on your clothing level and based on the activity level. Suppose even during daytime, during hot summer day, we do see cricket matches which are being conducted in the afternoon because their expectation is different, their mental state is different. So in all aspects, so the comfort ranges vary depending on the activity you perform. Then the steady state condition, which is basically the heat balance. So the outdoor comfort ranges are much wider when compared to the indoor comfort ranges. So these basically affects the activities that are performed in the outdoors. When it comes to necessary activities, irrespective of the outdoor condition, whether it is good or poor, we do perform the necessary activities. But when it comes to optional activities, it is significantly reduced when the quality of the outdoor environment and the comfort conditions are not appropriate. The optional activities are reduced significantly, but if it is enhanced, then the optional activities enhances. So, and there is minor variation in terms of social activities. So these uncomfortable outdoor environments results in spending less time in outdoor, and we hardly see people in the outdoors during daytime, and it reduces the social activities and also reduces the optional activities of visit to cafes or restaurants or any other outdoor spaces um, in terms of leisure or recreation. So to give a brief thing, in terms of indoor thermal comfort, the variation in terms of meteorological parameters are the ranges are quite less. If you see the diurnal variation in indoor and compare that with outdoor, the diurnal variations are much higher in outdoor. So if you see here, basically we can see that the temperature varies. Sorry. So you can see the temperature varies from about 31 degrees to about 27 degree. So there is a variation of about 4 degree variation. Similarly, there is a variation in terms of from about 23 percentage to about, from about 18 percentage to about 67 or 70 percentage of relative humidity. So these variations would create a different kind of thermal feeling or thermal sensation of in the human being. So basically, if you see, you can see within outdoor space, within a short space, spatial region, in terms of if you stand in between two buildings, there can be heavy wind speed, but if you just go to the street, the wind conditions completely differ. Similarly, you, standing under the shade, the comfort condition differs. Standing directly under the sun, the comfort condition differs. So there is a lot of spatial variation in the outdoor condition when compared to indoor. So these temporal and spatial variation creates different kind of thermal perception and thermal sensation in the outdoors. And also the wind conditions. So in the indoors, anything beyond 1 or 1.5, people cannot withstand, and they find it quite uncomfortable. But in the outdoors, people can withstand ranging from about 2.5 meter per second wind speed to about 10 meter per second wind speed. So it depends on what activity you are performing, your comfort conditions differs. So when you're performing fast walking or when you perform jogging, you can even withstand a wind speed up to about 8 to 9 meters per second. But if you're just relaxing, if you're just sitting, then you can withstand up to about 2.5 meters per second. So this is the kind of variation in terms of wind speed that we feel or that we perceive in the outdoors. So to give a brief on again, depending on the latitude, depending on the driver temperature, relative humidity, and wind speed, our comfort perception or sensation differs. This is an example of how the temperature and humidity behaves and how they yield to comfort conditions. If you see, this is in Lund, Sweden, wherein the tribal temperature variations are between 17 degrees Celsius to about 2 degrees Celsius, ranging from summer to winter. But you can see the relative humidity percentages that varies from about 66% to about 91%. So the relative humidity is quite high, but then we will not feel uncomfortable because the temperatures hardly crosses 20 degrees Celsius. Though the relative humidity is high, at lower temperatures we won't feel very humid, and it may not have a negative impact on the comfort condition. And you can also see that wind speeds here are quite high, ranging from 3 to 4 meters per second. So here it is the wind chill index that matters a lot rather than the humidex index that creates uncomfort feeling as such. So here if you see, this is the comfort condition. So you can see these these areas where you feel uncomfortable are mainly due to the higher wind speeds and not because of the higher humidity. Though the humidity is quite high here, the discomfort is mainly due to the wind speed and the temperatures and not because of humidity. Where in the same case, it was this is in case of Vijayawada. So all three examples that I've chosen are humid conditions. But then the first one is cold, humid. Here, this is hot and humid. You can see the temperature here ranges between 30, the maximum temperature is somewhere around 32 degrees and the minimum temperature is about 24 degrees. So we just have roughly around 8-degree variation between winter and summer. But the humidity ranges, if you see, it ranges from about 61% to about 81%. So though the humidity is lesser when compared to Lund, which is a cold, humid place, here the issue in terms of comfort is mainly due to the humidity and higher temperature. So the high temperature and higher humidity is causing the discomfort, and you can also see that temperatures here, the wind speed is hardly 1 to 2 meters per second. So the wind speed is lesser. The discomfort is mainly due to the higher temperatures and higher level of humidity. So here we can see these humidities, especially the temperature ranges. If you see here, it is somewhere around 22 degrees Celsius to around 26 degrees Celsius. Even at that particular 22 or 26 degrees Celsius, are we would find discomfort mainly because of higher humidities ranging at around 70% or 80%. This would cause a lot of discomfort in terms of outdoor conditions. So this is another place. This is Hong Kong. So this is basically warm and humid climate where you can see the temperatures are basically ranging between 16 degrees Celsius to about 30 degrees Celsius in summer. And here again, the variation in relative humidity is similar to what we saw in Vijayawada. This is somewhere between 65 to 76%. But then here the comfort conditions are comparatively better to Vijayawada, though the temperature ranges are 30 degrees and the relative humidity is similar to what we experience in Vijayawada. Here the temperature ranges are different, but then the higher wind speed, 3 to 4 or 5 meters per second causes enhances the comfort. So you can see here the comfort range is a lot of lines within the comfort range are mainly because of higher wind speeds. So here the issue, the what we need to look at it is not just the values, it is a combination of the temperature, the humidity and the wind speed. In cold climates, the wind speed creates a lot of wind chill index, but in hot climates, the humidity and higher temperatures lead to a lot of discomfort. So I think these things we have already discussed. The mean radiant temperature, basically when it comes to outdoors, during daytime we gain lot of temperature, like Dr. Fayez was mentioning, during daytime the MRT increase. So it is the basically the reflected radiation that one perceives during daytime. That's basically, so that would create a lot of heat gain in human body. During night, in the absence of solar radiation, we will lose heat to the atmosphere. So this is important. So mean radiant temperature is an important index which we need to look at, because that would define whether we are going to gain heat or lose heat to the environment. And as I mentioned, the temperatures, though the temperatures, if you see here in all three cases, the temperature is only 20 degrees Celsius, but the weather at that particular time. So this MRT also predominantly based on the weather condition on a particular day. So if you see at 20 degrees Celsius, if it's cloudy and calm, we would feel the same temperature. But the same 20 degrees Celsius, when we have higher solar radiation, which would result in higher MRT, which would result in heat gain. Though there is no wind speed, we would feel a temperature of about 30 degrees Celsius. This is basically the our comfort index in terms of PET. So the higher solar radiation, we would gain lot of heat. So we would feel as if it is 30 degrees Celsius. Similarly, with 20 degrees Celsius, when it is cloudy and if it is windy, then we would feel, though it is 20 degrees Celsius, because of higher wind speed, we would expect as if it is 15 degrees Celsius. So it also depends, the comfort also depends on the weather condition on that particular moment. So that also affects our comfort feeling or comfort sensation. So basically these outdoor thermal comfort studies, I think we have there are a lot of studies that have been done in terms of field surveys, then field measurements and simulation, which we have seen in all these 4 days. Here, these are the threshold values that have been. So, how do we feel? Because the thermal sensation analysis in indoor differs from that of outdoors. So, we can here you can see this is a standard threshold values defined by Matsarakis. Uh, Basically, here it ranges from less than 4 to 41 degrees Celsius. Anything beyond 41 degrees Celsius is termed as extreme heat stress. Anything less than 8 degree Celsius is termed as strong cold stress. So the generally here it is defined as 18 to 23 is the comfortable range, but this would differ in terms of Indian cities. So this is a study that has been done by Kotarkar, wherein we have defined the comfortable ranges have been defined for Indian cities where we feel extremely hot, especially in the tropics. So it ranges from, wherein in the previous study it is ranging from about 18 to 23. Here we are just, they have found that the comfortable ranges vary between 26 to 30 degrees Celsius, wherein there is no thermal stress. Anything beyond 50 or 51, it is termed as extreme heat stress, wherein in the previous other studies in other countries, it was only 41 degree. So here the heat stress varies from about 32 to 51 degree. It is categorized into slight heat stress, moderate heat stress, and strong heat stress. So these again, it varies based on the thermal sensation scale and thermal comfort scale, as well as thermal tolerance scale. So based on these, based on the number of points that you analyze, accordingly the ranges vary and it differs. So based on these, now we just go through some of the studies how these heat stress in outdoors could be mitigated through some design strategies. I think morning Professor Matt has given an elaborate indication of these landscape strategies, wherein these impacts. So if you see having a ground cover, I think even in Dr. Fay's study, we just realized the ground cover could not provide a lot of comfort. So the impact of ground cover is only to a range of about 10 meter, wherein the impact of group of trees and shrubs, it can impact the microclimate up to a range of about 60 meters. Similarly, the materials, I think yesterday we had Professor Matt presenting on a lot of these cool materials, how these, there were a list of 9 phase of materials which he discussed. So these materials used in pavement can also vary the outdoor thermal comfort. So and the ranges varies from local to city level. So integration of artificial structures like green wall, green roof, fountains can affect the at the local scale. At the street level, we can have the height to width ratio, which can impact the wind movement within the street level. At the public parks or open spaces, the tree canopy, ground cover, water catchment features at the urban draining level. And then at the city scale, the reflective materials on roofs, which we had seen several such case studies, which was presented by Professor Matt yesterday. So these will have an impact at the city scale. So the intervention can range from local to city scale, which can have a significant impact on cooling. Similarly, at the neighborhood level, we can either have canopies. I think we did see Professor Dr. Fayez mentioning about spacing between tree canopy. So that also matters because that also reduces the sky view factor. So which will also have an impact on thermal comfort. The portion of the um, uh, canopy that shade that will have better cooling when compared to areas that are completely exposed to sun. So then these kind of temporary shading structure, yesterday Professor Matt was mentioning about the dynamic shading structure, movable shading structure. We can either have static or dynamic, and the shade of these structure which falls throughout the day varies from morning to evening. So you can create these areas can be shaded. It cannot be shaded. It will not be shaded throughout the day, but at some point of the day, the shade keeps on moving. So the pattern of usage of these outdoor space can also vary based on the shading ranges. So exposed areas again can be enhanced by means of introducing water features so that it can add some kind of humidity into the atmosphere. Um, there are also other studies, like we had discussed a lot of these in hot and arid climates. Here again, strategies from 50% glass along with trees, 50% glass with 25% trees, and 50% glass with 50% trees, and 75% trees are underlined. Here again we can see when getting into these are basically simulated studies using NVMet software. We did mention these on-site measurements are important. Dr. Fayez also mentioned that these are important when we use simulation studies because it requires the validation is important. So when we simulate in softwares, we have to collect on-site measurements and validate those. Different strategies were analyzed, and the best strategies that improves the outdoor thermal performance were analyzed. Again, the parameters that are analyzed are like varies from individual meteorological parameters like air temperature and humidity, and also the comfort indices in terms of MRT, PET, UTCI, all that can be analyzed. So again, these are different strategies wherein we can see first in a neighborhood they just improved only 50% grass cover. The second strategy 50% scenario, basically 50% with 25% green cover. Then the third one 50% ground cover and 50% green cover, and 50% ground cover and 75% green cover. So we they performed this in a neighborhood, and the selected trees basically depends on the parameters that they have chosen are leaf area density, foliage height, leaf area index, and albedo. So these were selected, and then within these they've selected different within the neighborhood in different scenarios. They've selected 4 points. One location where they had pavement and tree only on shade on one side. Another location wherein it is between two building surface with asphalt road. Another location between two buildings but it has a pavement. Then the location where there is a green cover, grass, wherein the number of trees, the tree canopy has been increased again between. So they try to analyze these. So this is at location R1, how it performed in all three scenarios that were analyzed. So we can see that this is again our temperature reduction in terms of Kelvin. The temperature reduced during nights till about 6 a.m. Then it started increasing, and this again depends on the sun angle. This reduction after 6 a.m. to 12 a.m. Depends on the shade, mutual shading between buildings, and also depends on the sun angle, and it just elevates in the afternoon and then it decreases. And this varies with point to point depending on the shading condition in the night. So here you can see it reduced to about zero point 0.2, wherein here the reduction is only till about 0.4. So this is R2, which is this location, because again the tree did not reduce it. Here it was just open. So the reduction we can see up to 0.2, and there are some spaces of um, which are exposed to the sky, so it can radiate back. So again you can also see the reduction here. When it's here it is somewhere around 0.5 reduction in the night, ranging from zero point 0.2 to about 0.5. As the density increases, you can see as the density increases, the this is wherein 50% grass cover and 50% um, tree cover. So the temperature reduction is also enhanced mainly because of increase in relative humidity, this being an arid condition in Egypt. So these are different scenarios and different points. So you can see a reduction here of about, this is the base case, and you can see a reduction of from about 70 degrees to about 55, around 15 degrees Celsius reduction is there, but the behavior differs. Here it is only one side tree and it is a pavement. Here it is two side tree with asphalt. So here the second scenario did not perform well, but the other three scenarios performed well. Wherein here, which has ground cover, and then trees with ground cover and trees with pavement. So the ground cover matters a lot in terms of heat that is being radiated back into the atmosphere. Then these are some of the studies that have been done in Chennai. Now we'll just move on to some of the studies that have been done in India. So this is a study that was done in Chennai, a region called Tyagaraja Nagar, which is a mixed residential neighborhood. Here, similar to Dr. Faiz, we had taken three LZZ locations within Chennai, wherein this we try to analyze how the building regulations impact outdoor comfort conditions. So the first case provided the existing building regulations. So we just assumed that maximum built up with the existing building regulations. Then the same thing was introduced with increasing height and reducing the plot coverage. So that was the development regulations in Chennai was modified in 2019. So we tried to see what would be the impact of this modified building regulation, which had increased building height and increased FSI, while the plot coverage was reduced. So that gave way for a lot of open space at the site level, wherein here we considered the existing vegetation itself, and in case 3 we increased the open spaces that were available at the plot, converted 50% of that into vegetation and trees which are planted at an interval of 6 meter to 9 meter. So this increased the permeable surface fraction and the green cover fraction. So these were the three scenarios that were analyzed to find out which had the maximum enhanced outdoor thermal comfort conditions. So these were the three locations, and then we, in the first case, we could see these are the parameters as per the LCZ classification. So we analyze the sky view factor, the aspect ratio, the building surface fraction, impervious surface fraction, pervious surface fraction, height of roughness element. So if you see this, the height of roughness element increased with building height. So if you see here, the height of roughness element are lesser because wherein the building heights were much less. In case 2, the building heights were increased, but then vegetation was not increased. So the roughness element increased in the case 2, wherein here the building heights are increased and plot coverage increased, but retaining of existing vegetation. In case 3, the green surface fraction was increased, which increased the permeable surface fraction. So you can see that the permeable impervious surface fraction is the pervious surface fraction is increased significantly from the case 2, and the impervious surface fraction has reduced from case 2. So this enhanced the comfort. So we just try to analyze this, and these were plotted. So based on this analysis, so each the sky view factor again varied, because as the building height increases and the plot coverage reduced, the view to the sky also increased. So this is location A in the third level with lesser building and increased plot cover, the view to the sky was increased. So we can see that in the first case, which was the base case, the number of hours of extreme heat stress. This extreme heat stress is as per greater than 50 degrees Celsius, which is based on PET values. So you can see number of hours of heat stress in the base case was just 7 hours in the base case. In the improved case with 50% conversion of the plot area into grass cover and permeable surfaces, the extreme heat stress is completely reduced, and it is just gone into the moderate heat stress of 46 to 50 degrees Celsius, which was considered as moderate heat stress as per the recent study in India. So this has reduced the number of extreme heat stress in all three locations. So even in location B, which had just 2 hours of extreme heat stress, is completely reduced, and it doesn't even have moderate heat stress. It just reduced to only so this has significantly reduced to moderate heat stress or strong heat stress. So you can see that the duration of extreme heat stress has been significantly reduced in the modified building regulation by increasing the building height. Again, this depends on the compactness of the neighborhood. If it is compact, then that would vary. So if you see here, the LCZ classification varied with varying the building regulation. This was open mid-rise, and then location A remained open mid-rise, but in location B and C, which was a compact low-rise in the existing condition, was modified to compact mid-rise because of building height, and which was an open low-rise in location C has modified to open mid-rise because we had increased the building height but then increase the pervious fraction. So the local climate zone classification also varied. So that also will have an impact on the enhanced comfort conditions. So the next study is basically, this was done at Ahmedabad, wherein we did try varying some of varying the building heights in gated communities. So there is in Ahmedabad, especially near Charodi region, where the high-rise buildings started cropping up in the recent decade. So we analyzed what is the aspect ratio in the high-rise building, high-rise housing, which is a gated community, and we categorize them into three aspect ratio ranges. So aspect ratio range of 1 to 1.5, then aspect ratio range 2 is 2 to 3, and aspect ratio range 3 is 4.5 and 5, and we found majority of the buildings fall under the category of aspect ratio range 2 to 3. So we chose one of the high-rise housing in that range 2 to 3, and we measured on-site data, and we tried to validate through NVMET simulation, and we found a good correlation. Then we varied various scenarios by varying the building height. First, we tried to vary the building heights in northwest and southeast orientation. Then we modified the variation in southwest and northeast orientations. Then we introduced shading blocks between buildings. It could be this was in terms of just a pergola or a shade. It is not a floor. It is just a shade between the buildings. Like because we did realize that shading enhanced outdoor thermal comfort. Then we introduced it in the northwest southeast blocks. Then the similar thing was introduced in the southwest northeast blocks also. Then we varied all the heights of all the buildings, and we just analyzed these in NVMET simulation. uh, we did do the analysis for both critical summer and winter conditions for the entire day. So this realize, if you see, the first one was just higher building in southwest northeast, and the second one is north west and southwest southeast. So the third one with shading, then with shading in the other orientation. So we did find um, from the base case had about 6 hours of extreme heat stress, that reduced to about 5 hours of extreme heat stress, though it is just 1 hour. but then the variation, if you see, it has reduced to about 2 degrees Celsius. So from 52.4, it reduced to about 50.4, which is a significant reduction in terms of PET values, 2 degrees Celsius. But the same thing in winter, when we saw the winter also, they did have extreme heat stress of about 5 hours, which was significantly reduced to 3 hours in scenario 4 and 5. But then if you see scenario 3, though it had 6 hours of extreme heat stress, but in winter it was quite comfortable. So overall, scenario 3 performed better, but then here again we had a similar reduction if we of about 2 degrees Celsius, though it is the number of hours is same, but then reduction is significant. So these analysis has to be done for both summer and winter. Doing it only for summer may not be effective because we have to take it for a annual basis. So this was done, and then we did try to, using the best performing scenario, we did modify the same thing. So the existing was uniform height of all 4 blocks. Then we oriented in the best orientation with this northwest southeast. Then in the we just increased the height in the northwest, and then introduce a shading block in the northwest, introduce another shading block in the southeast. Then uh, then we perform the final. This was the proposed scenario. So this again was analyzed between the other case scenarios, and this proposed scenario which varied building height in all. Here when we vary the building height, there was just one consideration was considered. We had kept the FSI constant. We did not increase or decrease the FSI. FSI was kept constant. Only certain relaxation in building height was given. So normally in development regulation, there will be a restriction on maximum height to be built. So this we just relaxed to find out how this could enhance the comfort condition. It was not maintained as per the development regulation, but FSI was kept constant. Certain amount of relaxation were given in building height, but we did consider the air corridor and all that. That was not, it was not in the air corridor. So the height were increased, but then FSI were kept constant. So the saleable area remained the same. That did not vary. So with that variation, we could reduce from about 6 hours of extreme heat stress to about 3 hours of extreme heat stress, and significant reduction in terms of 2 degrees Celsius in the PET. And we also, that it also had impact on moderate and see, there is an increase in moderate and strong heat stress because we had reduced from extreme heat stress has gone to moderate heat stress and strong heat stress. Similar analysis was performed for winter also, and we found that the scenario had just 1 hour of extreme heat stress, but then predominantly throughout the day this was comfortable. So based on this, we suggest that varying building height, but maintaining the FSI, which is in terms of asymmetrical canyons, depending on the location. Here in Ahmedabad, the northwest and the southeast orientation performed better. So these were the findings of the study. So we could see a reduction of PET from 53.7 degrees to 39.3 degrees. This is in winter and this is in summer. So this, and then we because of the proposed no, this is in summer. So you can see this was reduced to about 39.3 degrees Celsius, and our MRT was significantly reduced. And even the PET in winter in the proposed state reduced to 32.7 from 59.7 in the existing scenario. So the proposal of 3:2 aspect ratio and northwest southeast orientation worked better in Ahmedabad scenario, but this would vary depending on the local geographic location and the wind direction. All that matters, makes an important needs to be considered for final recommendation as such. This is another study which was done in Vijayawada, which is again an hot humid climate zone. where we try to analyze the impact of sky view factor. Here also we vary the percentage of green cover and grass. Here we took two narrow, this is again a high-rise neighborhood wherein two pathways within the neighborhood which had a sky view factor of 0.224 and 0.342 vessel. This is the mean pathway and this is the space between buildings. We try to analyze how this could improve the thermal comfort conditions outdoor. So, is there some question or
Can take some questions actually. Anybody have questions? Ma'am's work is so we can ask questions, unlike Dr. Maths. So if you have any doubts, please feel free to ask.
any questions?
Yeah, no questions.
Can I continue?
Raghavi. Anybody? Raghavi, are you trying to ask something? If you're trying to ask, please ask or type in the chat box. Else, please mute yourself because we are not understanding whether you want to ask anything. I'm not able to understand. Either people, please either ask question or mute yourself because we are not hearing anything with clarity. Raghavi, Miss Raghavi Ilangovan, please mute yourself or ask your question. If you don't have a question, please mute yourself. The speaker is not able to understand whether you want to ask a question and then it is hampered. The talk is stopped now. Miss Raghavi, please mute yourself. Doesn't look like she wants to ask any question. Okay. So, chat box.
No. Okay. Can I continue?
Yeah, we can continue.
Yeah. So this study again, we analyze different scenarios and also we analyze different orientation of this particular neighborhood. This is the typical which had 5 blocks and a club house. Actually, the existing had 6 blocks. We removed 1 block to create space for open space there. So this is the kind of scenario that we analyze. The first scenario was 20% tree cover. So we analyzed in different
Madam, please, Miss Raghavi Ilangovan, please mute yourself. Sorry, madam, continue and write in the chat box.
Yeah. So
she's
we
muted.
did analyze 20% tree cover with different orientation, rotating this to identify which orientation works the best. And then we analyzed the same for various parameters like air temperature, mean radiant temperature and PET. And we found that the 225-degree orientation, that is the south, 225-degree orientation, which is the southwest orientation, worked the better because that created mutual shade between buildings, so which enhanced the thermal comfort. So then we did analyze for 50% tree cover. Similarly, we oriented and we found here the 135-degree orientation, that is basically the southeast orientation worked better. Similarly, 70% grass cover. We did not go in for 70% tree cover because that completely covered the sky. So we tried to analyze. This was taken from previous literature. Then we analyzed 70% grass cover. So this again gave 225 as the best performing orientation. So based on this, we did analyze PET. So we can see that 50% tree cover and 20% tree cover more or less perform better. But then here the reduction is significant from 52 to 48.2. So it's roughly around 4 to 5 degree reduction was there in 50% tree cover, wherein 20% tree cover we could get 2 degree reduction. Here if you see 70% grass cover, there was no reduction. Instead, it increased the PET values as we saw in Dr. Fai's study also. So the grass cover, suggesting grass cover actually increases the PET value, and it also increases MRT value. So it is always better to go in for trees, a combination of tree shrub, but then grass cover beneath the shade may work better, but then exposed to sky may not work better. So this is the analysis, and we can see that a temperature reduction of 1 degree Celsius up to 1 degree Celsius was derived from 50% tree cover, and a temperature reduction of only 0.1 degree Celsius was there in terms of 20% tree cover, and the temperature increased in 70% grass cover. Similarly, in terms of MRT, there is a reduction of about 4.75 degrees Celsius in terms of 50% tree cover, and it was 3.25 degrees in 20% tree cover, and the temperature increased in 70% grass cover. Similarly, a reduction of 2.5 degrees Celsius was observed in terms of 50% tree cover in PET, and 1.6 degrees Celsius in terms of 20% tree cover, and the temperature increased in 70% grass cover. So the study, after doing this, we realized that a reduction of 1 degree Celsius with 50% tree cover, how this could impact the energy consumption in indoor. So we just model using this meteorological condition at this scenario. We reduce the values of our temperature by 1 degree in the microclimate in design in the EPW5, and then we ran the simulation in Design Builder to find the energy consumption, the indoor energy consumption pattern during summer and winter. And we categorize the building into 3 levels: the lower levels, middle floor levels, and upper floor levels, because the energy consumption pattern also varied with the number of increase in floors. So we can see that during summer, though the reduction, this is just done for 1 day, but it has to be done for monthly basis. We just ran the simulation for 1 day for want of time, but then this, if it is run for a month, then this can be run better. So here we just multiply that into number of units for a monthly basis, and we found that this is the saving on a monthly basis at different floor levels. Though this is lesser, the cost during summer depends on the total number of energy consumed per month. So energy units consumed, as the number of unit increases, the cost is also increased, because of which the this is the savings that we get got during the study, and it varies, and it is, the saving is much higher at higher floors when compared to lower floors. Similarly, in winter, the savings were much higher. So the reduction in number of units is much higher, but it is more or less the same in all the floors. But since in winter the total number of units consumed are much lesser when compared to summer, the cost reduction is per unit is much lesser. But then if you can get much better significant reduction in winter when compared to summer, because the summer temperatures in Vijayawada are quite high. It ranges from about 38 degrees to about 43, 44 degrees during daytime. So without air conditioning during daytime, it is not at all possible to stay indoors. Because of that, the summertime savings are much lesser. But in winter, if the microclimate is modified, that can enhance the energy consumption, that can reduce the energy consumption pattern, and it can enhance the energy savings. So we can save much, because the summer temperatures in Vijayawada is somewhere around 34 degrees Celsius, and if that can be reduced by about 1 degree Celsius, then it will have significant impact on energy savings as such. So this was another study done at Vijayawada. So we can see the savings in terms of, so the middle floor had better savings in summer, wherein the upper floors had higher savings during winter. So here, as far as Vijayawada is concerned, the 135-degree north orientation, that's basically the southeast orientation, enhanced comfort. That's mainly, it minimized sunlight exposure and it maximized the wind speed. Being hot and humid, the wind speed played a significant effect in enhancing outdoor thermal comfort. And generally, these gated communities had a maximum building height of 24 meters. So a 13-meter spacing was suggested between buildings, which will include 2.5 meter spacing between buildings and the uh, uh, vehicular movement or the road. So that can provide, that can integrate greeneries or vegetation or trees within the gated community, which can enhance the thermal comfort conditions, especially in the outdoor, which will again have an impact on indoor energy consumption also, that can be reduced significantly. So that was the finding of this particular study. And there's another study which was done at Ahmedabad, especially in low income settlements. Here, it was found as a hotspot in Ahmedabad. We analyzed 4 different clusters here, wherein we tried roof level, pavement level, and in the wall levels. So we modified different materials in the roof, which had higher albedo of 0.7 and 0.8, 0.95. Then we also had medium albedo in terms of 0.3, 0.3. These are the different materials that we use. So we mainly, the study had concentrated on higher albedo. So we just categorize. HR indicates higher albedo, M indicates medium albedo. So L indicates low albedo. So these were the options that were used in pavements, walls, and then roofs. So then we tried to replace it with the existing condition, which had brick wall and GI sheet roofing, and some of them had asbestos, cement, and concrete pavement and bare soil. These were the existing conditions. So we did simulate different conditions here. So here, the first case was medium albedo in wall, medium albedo in roof, and low albedo in pavement. And these were the mean radiant temperature values. So here, these options or scenarios which had medium albedo in wall, lower albedo in wall perform better with lower pavement. So here we realized that the walls and pavement should have predominantly lower albedo, as they reflect heat onto the streets. And the roof, since this is a low-rise development, this suggested medium albedo is much better. So if you see here, from here there is a reduction of about 1 degree, but then though 1 degree reduction is very less, but we can see this reduction in terms of MRT was reflected radiation, it was much better. So the other three clusters wherein we can see here the medium albedo in wall, the medium roof and medium pavement perform better. So we can see that the maximum temperature, the ranges have predominantly, these are just moderate with just 1 hour with extreme heat stress. So we are just looking at the number of hours of extreme heat stress, reduction in that, because you cannot reduce the heat stress throughout the day. So the intent is to reduce the total number of hours of extreme heat stress rather than looking at removing heat stress from that location. That is not possible with the higher temperatures and humidity that are experienced in tropical regions. So here we were able to reduce the extreme heat stress to just 1 hour from the base case, which was approximately 4 hours. So that is the kind of approach we had done it. Here again, in this particular cluster, we could again medium albedo work better. So this study suggested that low-rise informal settlements going in for higher albedo as they reflect heat into the atmosphere and which are trapped. It acts as a heat trap, and due to convection at the lower level, the street level temperature or the mean radiant temperature comfort level was very hot. So if in high rise, then going for higher albedo is better, but in low rise, especially G+1 structure, going for higher albedo in the roof may, due to convection, it might increase the heat sensation on the street. That was the finding in this particular study. Yes, I think with this, I would stop here. Thank you for your attention. If there are any questions, I can just.
Anybody has any queries, any questions, or any aspects to discuss?
Yeah, good afternoon.
Good afternoon.
Yeah, I have one question actually, ma'am. You have talked about the indoor thermal comfort and outdoor also.
Yes.
In Indian context, do we have any national standard for indoor thermal comfort, like say in RCC roof or tile roof or tin roof? The temperature should be range between this degrees Celsius, and that need to be followed by different departments like housing department.
No.
Do we have? Yeah.
No, we do have standards in terms of thermal comfort range, indoor thermal comfort range. But in
Okay.
terms of temperature of materials, we don't see this is basically defined in terms of thermal comfort range rather than the temperature on material. You're talking about the surface temperature and different
Yes.
materials. Because that does not define that, because again thermal comfort depends on the overall comfort range. So we'll have to follow the thermal comfort range. IMAC stipulates operating temperature for various cities. So based on that, based on IMAC only, we analyze these studies. So we did, based on the operating temperature range, we were trying to see whether modifying these material assembly in the building envelope can enhance the comfort within, can bring down the comfort within that comfort range. That is the
Okay.
intent.
Okay.
But in terms of surface temperatures, there is no standard as such. But in terms of comfort ranges, there are standards. ASHRAE standards are followed, and for Indian cities, IMAC is generally adopted.
Okay. Thank you.
I think so Vijay Lakshmi can add on to it because it's on indoor thermal comfort.
It's your day, ma'am. Enjoy. I'm like dumbfounded after the first class.
Yeah.
I
How
don't know.
to select the appropriate thermal comfort index for city scale that works both indoor and outdoor. See, the thermal comfort index, it depends on the climate type basically. So, not all thermal comfort indexes suit the different climate types. So, for especially humid climate, the index that includes humidity as an aspect need to be considered. So, generally, for tropical cities, PET, UTCI are generally adopted for outdoor thermal comfort, as well as in terms of indoor thermal comfort, it is basically the operative temperature which we use. Yes, Aishi, did I answer your question? Miss Aishi.
Yes, thank you, ma'am. Yeah. But ma'am, in addition to that, I also wanted to know, say, if I'm comparing between the city level phenomenon of across different climate zones, would I need to calibrate those values so as to say this is equivalently comfortable or something?
Within the same city, you are trying to say at different neighborhoods?
No, yeah, that, and also for different climate zones, for cities in different climate zones, if I am to compare the comfortable conditions.
So different climate zones will have different comfort ranges. So you'll have to first identify the comfort ranges for that particular climate zone or for that particular city. And then you'll have to compare your results with that particular comfort ranges. For example, in Vijayawada, even 32 degrees, 31.5 is considered as comfortable in terms of outdoors. But for indoors, we don't go beyond 28. So it all depends on the comfort range. Cities and the type, whether it is in indoors, it depends on whether it is a naturally ventilated building or if it is a conditioned space. So based on that, the comfort ranges differ. So based on your study condition and based on your assumption, you'll have to derive those comfort ranges and then compare your findings.
Okay, thank you, ma'am. Yeah, got it.
Any other question? Dr. Vijay Lakshmi, Dr. Prashanti,
Yeah.
there
Yeah,
are no
yeah.
questions,
So,
can we mind them?
yeah, okay. Since there are no more questions, thank you, Dr. Lily and Dr. Faiz. Thank you so much. And we will meet again tomorrow, which will be the last day of the GYAN program. It will be the 5th day. So please be on time. Otherwise, you will miss important things that are told. Okay. So be on time and we will meet tomorrow. Thank you. So tomorrow's session starts at 11. It's only by sir and it is 11 to 1. So be on time tomorrow. Thank you. So, join at 11 o'clock tomorrow, 11 to 1, and then we'll have a small valediction which is online. Thank you, Brindaji. Thank you so much. Bye. So I will log off. Thank you.